Okay, guys, we're gonna knock out the rest of this AC/DC stuff and move on. So, AC versus DC, we talked a lot about it today. We've got alternating current versus direct current. At the end of today's lecture, I talked about current generation. A generator motor needs to be spinning and produces the current through induction. Now, don't be afraid of induction. That's our friend, and we will be talking. We'll be talking more about induction later. So that would be an electric motor running in reverse. So a generator and a motor are essentially the same thing. One takes kinetic energy and moves it. We've got the kinetic energy and we're transforming it into electrical energy. And a motor takes the electric energy and it transforms it into kinetic energy. So this would be a generator and this is a motor. But all you're doing is you're flipping it around. You take the generator and then you say, I need to convert my electrical energy to kinetic energy. So I take my generator and I hook all the wires backwards. And then I have electric motor that will take that electric energy and turn it into kinetic energy. Drive my car or whatever. Okay, so that's current generation for AC. And then for DC, we've got batteries, fuel cells, solar panels. We talked about those things a little bit earlier. Batteries some can be charged up, some can't. Fuel cells, we're not going to get into that a whole bunch, but it's very useful, and in the future we might have, probably will have hydrogen fuel cell cars. So you can look into fuel cells if you're interested. Of course, solar panels are excellent way to convert solar energy into DC power. Okay, so we've got our spinning turbine, and for our AC generation of current, and it has a frequency. The spinning turbine will spin around a certain amount of times per second, and it produces a certain frequency. In the United States, that is 60 hertz, and then in the Europeans, they have 50 hertz that they produce, and 1 hertz is just 1 cycle per second. So you guys know about frequency and hertz and all that. So I think we're pretty good there. So let's get into example 2010, and we'll start talking a little bit about power, transmission lines, all the stuff that we really need to think about. I was going to draw out some transmission lines, but okay, so let's say we have okay. Let's say that we have a generator station. Okay, so here's where we're generating our AC power, and the wire goes out, goes to the big, huge tower. And then that goes to the next tower. And so forth, ... all the way till we get to your house. I don't know where you live. Okay. All the way to a transformer in your neighborhood. Let's do that. Okay, so whatever. some transformer that is going to step down the high voltage to go to your house. It'll get transformed, and then here's your house, and that power will go inside your house and run your lights. Okay, so given a voltage of 200,000 volts, okay, so 200,000 volts, 2 times 10 to the 5 volts. Okay, that's our voltage that we're supplying here at the beginning. We want a power transmission, so we want to transmit the total power that we're going to transmit is 100 megawatts. Okay, so we want 100 megawatts. Of course, we're not. All right, hold on. Where's all that power going? Not to just one house. This transformer here feeds a whole neighborhood. It feeds many neighborhoods. I don't know. It feeds all kinds of houses. So we're not going to just do your house with 100 megawatts of power. So anyway, that's how it works. It gets distributed from that point. But at any rate, we want to transmit that much power from this generator at point A to the point B station. It's a transformer station, is what it is. Okay. Awesome. So far, so good. Now, we've been given this number, and we've been given this number. And I told you in class what to think about those numbers. And hopefully you'll remember what I said, and that is that when somebody gives you a voltage like this, then that voltage is truly the VRMS. Okay? If they don't say it's the peak voltage, then it's your VRMS. The power transmitted is this 100 megawatts, but that is also equal to our power average. Okay? Not the maximum power. All right? So unless they say power maximum, it's not the power maximum, it's the power average. Okay, so VRMS and power average if they don't say anything else. All right. Great. So what is our current in this situation? Well, that's pretty easy. We've got our P average is equal to our IRMS times VRMS. And we can solve for IRMS pretty easily. We'll just take our power average and divide it by VRMS. So 100 megawatts. Let's see, that's 1.0 times 10 to the 8 watts, and we're dividing by 2.0 times 10 to the 5 volts. Okay, so IRMS, that's equal to 1/2 basically times 10 1/2 times 10 to the 3, and then watts divided by volts has to be amps. Okay, so unit wise, watts over a volt 1 watt over 1 volt equals 1 amp. Okay, so there's our units. If you need, but current is always in amps, and if we use watts and volts, we are in the SI system. So good. So 1/2 times 10 to the third, what is that? That's really 500. 500 amps. Okay, so that's our IRMS. All right. Now, our next question is, let's move up here a little bit. Our next question is, let me get this right. What is the power dissipated? What is the power dissipated? What do we mean by power dissipated? It's power lost. So I'm going to write dissipated, but then I'm going to make that equivalent to power lost. Okay, so what is the power lost if the whole resistance, the resistance from A to B is 1 ohm. So let's do R equals 1 ohm. So these are big old cables. Maybe they only go, I don't know, 10 miles or something, but the resistance all along the way from there to there is 1 ohm. Okay, so we're gonna move back. What is the power lost if the transmission lines are, or have, we don't want are, we want have here, have a resistance of 1 ohm. So how do we do that? You guys already know. Power loss. So here's a couple of things that you want to keep in mind. If you're ever asked for power lost or power dissipated, it's your P loss. Okay, P loss, that power loss, you always want to figure out what is your current, and you're going to square that and multiply it by your resistance. Okay, just do it that way. Don't work with voltage when you're dealing with power lost. Okay, you may end up getting the wrong answer. Figure out what your current is. Unfortunately, it's just the best way to do it. Power lost is your current squared divided by, or multiplied by your resistance. So we're going to square this current. We're going to square 500 amps. That's a lot. 5 squared is 25. 100 squared is 10,000. That's 25,000. And it's nice, our resistance is 1 ohm. So we can say 25,000 watts. Now let me make sure I've got that right over here. Dang it. How did I miss an extra zero? 500 squared. Sure enough, I missed a zero. Okay, so it's 250,000 watts, okay, or 250 kilowatts. All right, that's how much we've lost. But we wanted to transmit transmit this, I don't know why I put two T's on transmit, the 100 megawatts. Okay, so 100 megawatts is what we really wanted transmitted. So our next question is, what is the ratio of power lost to power transmitted? Okay, question mark. Ooh, this is where if whiteboards only did this right there, I could do. Okay, so what is the power or the ratio of the power lost to the power transmitted? So simple, you guys know how to do that. Let's move up a little bit and we'll do our 200. I'm going to do ratio equals 250 over 100. And the best thing to do at this point is to just write it out. So 2.5 times 10 to the 5 watts over 1.0 times 10 to the 8 watts. That leaves us with 2.5, because 2.5 divided by 1 is 2.5. And then we're going to multiply that by 10 to the minus 3. And if we want the percentage, then that percentage, let's see, let's move some decimals over. There's minus 3, I think, is this. Let's see, 1, 2, 3. That does it. So it's 0.0025. Now, if we want a percentage of that, we multiply by 100, and so the percentage is 0.25%. Okay, so we've lost 0.25%. Now this is what I want you to compare. We're going to compare this. We're going to do the exact same thing. We're going to ask the same questions. We don't need to ask what the current is. Okay. Oh, no, yes, we do. We need to ask what the current is. Okay, so we're going to change. We're going to go from this voltage here, instead of 200,000 volts, which is a lot of volts, don't touch that wire. Okay, so we're going to go from 200,000 volts, we're going to go down to, let's see, what did I write? 10,000 volts. So 250,000 down to 10,000. 10,000 volts is still a lot of volts. Okay, but we're going to do the exact same thing with our voltage. Our VRMS is 10K volts. Okay, and we still want that same power transmission of 100 megawatts. All right, 100 megawatts of power. And we're going to, let's just do it. Let's just solve P equals IV, and we'll solve that for our current. So this is A. Our current is equal to our power divided by our voltage. 1.0 times 10 to the 8 watts, and we're going to divide that by 1 times, in fact, I don't like putting the 1 on there. It's just 10 to the 4. 10,000 volts is 10 to the 4 volts. So we end up with 10 to the 4 amps. Okay. 10 to the 4 amps. Great. B. What was B again? I don't know. We want to know the power loss. Okay, so power lost. In order to get the power lost, we found out what our I is, so we're going to square I and we're going to multiply by R. The R is the same old R. It's still 1 ohm, okay? So what's our power lost at this point? Well, it's 1 ohm times 10 to the 4 amps, and that's a watt. Oh, no, it isn't. Okay. We got to square 10 to the 4. Have you ever done that? That's 10 to the... how come I'm losing my brain? 10 to the 4, square that thing. Yeah, 10 to the 8. I just thought, man, that's a big number. All right, so 1 ohm times 10 to the 8 squared amps ends up being a watt, by the way. So we've really got 10 to the 8 watts. So every single thing that we did, every single thing, what's the ratio? Well, the ratio of power lost to power transmitted is equal to 1. We lost every single bit of the power that we wanted to transmit along the way with just 1 ohm as our resistor. Okay? So 1. And if we multiply that by 100%, we end up with 100%. Okay, so 100% power loss. So this is the whole point, okay? This is the reason why we want to kick up our voltages to be very high, okay? So the higher the voltage, this voltage right here, let's point it out in green. That voltage needs to be high or large. Okay? Needs to be. The smaller it is, the more loss we're going to have. We can't have smaller amounts. So 100% power loss, that is no good. we are in trouble if that's how we're going to roll. Okay, so what's our next thing? What are we hitting up next? All right, so this leads us to the transformer situation. Go back to black here. All right, so transformers. Step up voltage or step down voltage. And we will be talking about transformers for sure. Just on a side note, I told you that we could do the same thing, direct current. We could do the same thing. it's the same power loss. It's the same. All that stuff is the same. But with DC, if we need to step up or step down, DC transformers are expensive. Not it. I mean, it's so unwieldy that it's terrible. Okay, so DC, in order to get high voltage DC, is very hard. There's another way you could do it. No. Now, this is just very difficult. Okay, so it doesn't happen. But with AC transformers. In fact, they don't even call DC transformers. I'm doing it because I don't want to complicate things. We're not even going to talk about it. After this point, DC transformers, high voltage will be the thing that we use, and it'll have to be AC, okay, because this is just not happening. So AC transformers are the way to go because they are cheap and easy, I guess they're easy to make. Not expensive. So that's basically the whole reason why we do it. Yeah, I don't even want to go into what it requires to do DC. That's too much. We'll just leave it at AC is the way to go when we want to transmit large large amounts of power. So let's wall that all off. We'll wall that off. And we'll start talking about the dangers of electricity. You guys probably know that it's pretty dangerous. You've probably been shocked yourself, either with DC or AC. I'll tell you guys a story about my experience on Monday, because I don't want to do it here in public. I mean, who knows who's going to watch this video? I'm embarrassed. No, not really. It was dumb, though. Okay, so anyway, there are thermal hazards. Okay, so I think this is worth discussing. So let's say we've got some voltage and it comes down and it goes to a plug in the wall. Okay, so we've done this. We have some plug in the wall and we plug our appliance in to that plug, and let's write plug here. And then it runs over to our toaster. Let's make it a nice toaster. And on the inside of that toaster, of course, the current is going to run in, and the toaster is our load resistor. Okay, so that's essentially, I've turned the whole toaster into basically a resistor. Okay, that's what it is. It's a load resistor, our RL. Okay, everything in this situation runs perfectly. All right, we've got our resistor on one end, we've got our supply on the other end, everything's fine. But now our wire is kind of going bad a little bit. It's kinked in a certain spot, and there's I don't know. It's just kind of gross. Things are falling apart, and the insulation between the two wires, one going one way and one going the other way, are to the point where they're basically trying to connect. So I don't know if you can see that. I just drew a little bitty tiny connection. So it's a very fine little connection. That little connection between there allows some of the current to go that direction instead of going through the toaster. Okay? And let's say that our appliance load, RL, is 35 ohms. Okay? And the wires in the cord aren't insulated. Who knows what happened? And we've got some resistance here. I'm going to call it R. This little R. That little resistance is 0.1 ohms. Okay? So, it's bad, right? This is bad. It's bypassing our on-off switch, because the on-off switch for the toaster is over here. Let's make a switch right here. So here's our toaster switch, meaning that even if the toaster is unswitched, it's not on, right? The toaster isn't, there's nobody pressed the buttons down, there's no Eggo muffin in there, Lego my Eggo, all that stuff. It's not there. What's happening is current is definitely flowing through here all the time. Okay, so the current is doing its thing all the time, 100% of the day. This is a bad situation. That's the first thing. Second thing is we're going to talk about the power lost. So we've got power. Do you guys know what our normal voltage is for our houses? 120 volts. Okay, that's our our VRMS. All right, so VRMS. Now, the power, I'm going to use voltage squared, okay, over R. But we're going to do voltage squared over the little r. Okay, not the load. We're going to do it over this little r. And so that's 120 squared. And of course, we're going to end up with watts divided by 0.01. And that's 144 kilowatts. Okay, so that's a lot. All right. Now, if we look at what it should be, then we're looking at, this is the short. And what it should be normally is our power is, let's do it, 120 squared divided by 35 watts. And I don't know why I don't have that written down in my notes, but 120, we're going to square that, and we're going to divide by 35. 411. Okay? 411 watts. So a toaster, and these are actually pretty good numbers. All right, this is a good number for a toaster. Toasters use up quite a lot of watts. They don't do it for very long, all right, but they do. And if look at how much power is lost if we allow this short to continue. And it's just seriously power being lost all the time. Okay, this is where heat starts to come into play. Things start to go south really quick. So heat this right here produces a lot of heat. Okay, so when the fireman comes to the house that is just burned down in your neighborhood or whatever, and they go in and they do their inspection and try and find out where the fire started and all that stuff, which they're extremely good at, and they will find out where the fire started. They'll figure out which wire burned your house down, and they'll note, and they call it a short. Okay, they'll say, oh, that house burned down because of a short in their wire. This is what we call a short. Okay, so how do we protect against this from ever happening? It's a dangerous situation. Well, we have fuses and circuit breakers. All right, so fuses and circuit breakers. A fuse, I'm going to draw a fuse for you guys. So here's one end of the fuse. It's metal. So we got all this, we got metal here. We've got another end of the fuse over here. And it's metal. And then inside the fuse, there's, let's keep it black, I guess. There's this section where only so much current can go through this section right here. It's neck down so that they limit the amount of amps that can go through this fuse. Okay, so on one end, we're connected to the wire that goes to whatever, to the power, and then this goes to our object. Okay, and then this middle part, of course, this is sealed, vacuum sealed. And then this part in the middle will definitely blow, and it blows because we don't want this to get too hot. We don't want this, gosh, get control of yourself. This bit right here, we don't want that to happen. So what will happen is before this short can do its thing, this fuse will break. Okay, the fuse here will break the circuit. Okay, then I don't know if you guys have lived in old houses or I don't know, they're still around, but what you got to do is replace that fuse. You got to put another one in, right? So you got to replace this fuse every single time it breaks. And if you you don't know you've got shorts around the house. You're like, all my wires are old, all my toaster, my microwave, all those things are old. I don't know which one of those has the short. So you end up having to replace your fuses all the time. because your refrigerator's old or whatever, and you really should be buying a new refrigerator, but who can afford that? So fine, that's fine. That's where circuit breakers come in. Circuit breakers are nice because a circuit breaker is a switch. Let's see, how do I want to draw this? Do I have a good drawing here? I don't have a good drawing of a circuit breaker. Let me think. Okay. If it gets too hot, it's going to bend. Okay, so here's how it works. It's a black box. Well, it is a black box, but okay. How do I want to do this? First of all, there's a switch. So we've got this switch that you can. It will drop down. So, this is turning out terribly. The switch will fail, and that disconnects this circuit. So the wire comes in, and a wire comes back out here. And if this fails, if it gets too hot or too much current is going through it, then this drops down, moving this switch up. Okay? And that breaks the circuit. All right? So it's a circuit breaker. And it's got a galvanometer spring in there that, I don't know if you guys know about pieces of metal that are, one side of the metal is one type of metal, and then the other side of the metal is some other type. And because they have different coefficients of elasticity and all the other stuff, and temperature dependence, as they heat up, one will bend more than the other. So this blue one wants to bend more than the black one, and it'll pull the switch away. In fact, let's change our arrow to be an away from. Okay, so imagine this thing then curls away from our connection. Then you can flip it down like this. You flip the switch down, and it replaces it. It puts it back up. It pushes that wire that has now been broken back up. That's actually not a bad description. So that pushes it back up and connects it again. If you're in a situation where you simply have too much going on, too many shorts or too many whatever in your wires, your wiring's bad, it'll fail immediately again. So you're basically forced to fix the problems. You just can't do it over and over. So let me put the blue part in here. So the blue side is here, and the black side would be here. Okay, and so then you just reset it. You just push this back up, and everything's fine, but you probably should fix your stuff. Okay, so the metal has known resistivity length L, blah blah blah. Okay. Let's do that. Let's do that. We've got case 1. All right, so here we've got some appliance. First, I just want to write P equals I squared R. All right, I want to get that off my chest. But we've got something, whatever the appliance is, and it's old, damaged, whatever. It's seen better days. Our appliance. And the resistance, what it used to be, new, R equals 0.1 ohms. Okay, but over the years, it has increased its resistivity, as things do, to 2 ohms, right? That's a lot. That's a big change, 20 times larger resistance. Still works. Everything's fine. Everything's going okay. But let's look at our power in this situation. And if, let's say, the current is always 10 amps, our current is equal to 10 amps, then we're going to square that current, get 100. And if we have 100, so in the new, 100 times 0.1 is 100 times a tenth, that's 10. Okay, so 10 watts new, but old, we're dealing with 100 times 2, that's 200 watts. So new appliances versus old appliances, you're going to have changes there as well, okay, simply because the resistances for the objects are going up and down. What if our current supplied is too much? So here, let's look at case 2. Too much current. So we still have this brand new resistance equals 0.1 ohms. But our current isn't the 10 amps that it's supposed to be, it's 100 amps. Okay, so at that point, our power, I squared R, that's going to, squaring 100, that's 10,000 times 0.1 is 1,000. So we've got 1 kilowatt. 1 kilowatt is a lot compared to what we would have had as 10 watts. So this is, again, another bad situation, providing too much current to a certain object. So fuses and circuit breakers allow us to keep this from happening, right? These objects won't allow more power than we're supposed to have go through them. I should say current, right? current limited. So you can get different ones. You can get 5-volt fuses, 10, 12, 100. You can get all kinds of fuses. And the same thing goes for circuit breakers. On a house, 15, 30, those are common. Sometimes you'll see a 20 amp fuse. So yeah, those are common. And call the electrician if you don't want to handle it yourself. I actually handled my own electricity. That's how I got shocked, because I'm not afraid of electricity, and live by the sword, die by the sword, I guess. And so hopefully I don't die trying to fix my basement. Okay, so all of this stuff can happen to people instead of wires, right? Because anything can transmit electricity. If you have enough voltage across it, that thing will break down, okay? So our bodies actually are pretty good transmitters. Why? Because first of all, we're made out of water. And alone, water is an insulator. Okay, alone. However, water gets contaminated very quickly, and even though we're 90-something% water, is that right? 93% water. Human is I don't know, 90. I think it's 93%. I might be wrong. I've got all kinds of crazy facts in my head that I mix them around. So I don't know. I think we're 93% water. Correct me if I'm wrong, but it doesn't matter. We're a lot of water. 73, 93, somewhere in there. We're a lot of water. So, but in a human, that water is kind of contaminated. In fact, we're much like the ocean. Ocean water. Well, what does the ocean water have in it? Salt. Salts, Na sodium chloride, and potassium chloride, those kinds of things we are full of. So it's not pure distilled water anymore. Pure distilled water is an insulator. As soon as you start mixing things into it, salts and whatnot, which is our human body, then all of a sudden you have a very good conductor. Very good conductor. Not great, but we definitely have the ability to conduct electricity. So, all right. So, also we've got nerve endings that transmit chemical and electric signals throughout our body. There's all kinds of things that can happen. But these are electrolytes. Electrolytes. And those electrolytes are what allow the transmission of electricity, okay? So there are 4 factors that make an electric shock through humans bad or worse. I mean, it's bad. So you start off with bad, but it makes it worse. Okay. So from bad to worse. So the first thing is the amount of current. Okay. So, and this is really huge. The amount of current going through you. I mean, we just saw above how the amount of current really delivers a lot more energy quickly because of the power goes up as I squared, right? So that's bad. But then there's the path of the current. Let me just write P equals I squared R. The path of the current. And here, what I'm talking about is, so we've got, you could have it go through, I don't want to draw a picture of a person. Here's the person. Here's their arms. They're doing the wave. There's a couple of things. What could happen? You could have the connection from the head to the foot, right? That's bad because it runs through your heart. Okay, also your brain, right? We've got a brain in there. And we don't want it to do either of those things. You could have it run from your left hand to your right hand, again, going through your heart, right? So that's bad. Now, if you just had it going from this foot to this foot, so it goes in here and then out here, not terrible, okay? So that's not the worst thing that could happen to you unless it's, 10,000 volts, right? You do not want that. But if it was, a fairly small current, very small voltage, you'll be okay, right? It would pass through you fairly quickly. Hopefully you would be able to get out of that situation quick, whatever. You really just want to keep that current from going through your heart if you can, right? We don't want it going through our heart. Your heart gets upset pretty easily, by the way. So 3, I kind of mentioned this, the duration or time. For the shock or of the shock. So if you can minimize the amount of time, of course, do that, right? You want it to last as short as possible. And then lastly, the frequency. So, oh boy, frequency. AC, we're going to have 60 hertz, and DC, how many hertz? No hertz. So I'm not saying DC isn't going to kill you, but AC will kill you faster. Okay, so this is bad. This is not so bad. Okay, so there's table 20.3, and I've got my book here. Hold on, let me see if I can get to table 20.3. Boom, boom, boom. Why don't I even see it? I don't know. Where's this table they keep talking about? Is that it? Table 20.1, table 20.2. Where's table 20.3? Did I write down the wrong table? Coefficient alpha, no, that's definitely not the table I'm looking for. You're not the droids I am looking for. There it is. It's on 868. Okay, so page 868 has table 20.3. And it talks about the different currents. Okay, that is the very number one thing that will be the worst part, right? Even a very short, if it's a large current, you're in trouble. So table 20.3 talks about the different currents. So let's go, I'm not going to write them out because it's already done, but there's the threshold of sensation. So at 1 milliamp, you're going to notice with your skin. Harmless current, 5 milliamps. 20 milliamps is the onset, 10 to 20, is the onset of sustained muscular contraction. So have you guys heard of a TENS unit? They've got these things called TENS units. And a TENS unit, if you get into physical therapy, you'll know what I'm talking about. It's on your skin, they put these electrodes, and then the muscles, so here's your skin. You'd put an electrode here and an electrode here, and then it produces a current through that makes contractions in your muscles. So your muscle here would contract depending on what the TENS unit is doing. You can set it up to vibrate or do all kinds of stuff. So your muscles will contract and excuse me, release and contract very quickly over and over and over. That's the sustained muscle contraction. So a TENS unit operates in the 10 to 20 milliamp range. 10 to 20 milliamps. You can crank it up to 90 if you want, or I don't know. I don't know how they work, but they're out there. You don't want to do it for very long. I don't know. Maybe even a TENS unit will operate around 5 milliamps too. I'm not 100% sure. At 50 milliamps, that starts to hurt. All right, 50 milliamps hurts, and then 100 to 300 plus is bad. 100 to 300 plus is worse, but in this range of milliamps, you can get ventricular fibrillation, which is basically your ventricle fluttering. Okay, it just starts to spasm. Okay, it's a heart spasm. And it's not, heart spasms are bad, right? Because your heart has a very regular beat. If it starts to quiver, instead of doing its sinusoidal whatever, I used to know what it looked like. You've seen them. You've seen the graph where it comes up and it goes down and then it goes like this. And then it goes up and it comes down and goes like this. Okay, that's what it should do. But when it's spasming, it's going like this. And you're not getting any blood flow, right? Soon dead is what happens in that. That's why AFib is bad for you guys. Take it from me. All right, so what do we have past that? We've got Onset of burns, 300 plus milliamps. You're going to get burns on your skin. Okay, bad. 6 amps. Let's go all the way up to 6 amps. Okay, so limit this as much as possible. At 6 amps, you are in trouble. You can die in this situation. These will kill you. 6 amps will for sure kill you. What are they saying here at 6 amps? Your heart basically stops beating. It freezes up. Total contraction. Okay, it just seizes. So your heart goes, and however, you can do one of those defibrillators and possibly get it back if you stop the current flow. And then you guys, seriously, it goes up from there. And there are videos online and stuff where you can watch people get electrocuted. It's terrible. It is really, really terrible. So I don't know. Just be careful with electricity. The last thing I want to say before we go, before I stop here on this wonderful note, is that section 20.7 we aren't doing. Okay, so we're not covering it. However, for biology students, you should read it. Okay, so section 20.7. That's a 7, by the way. I don't know why I draw 7s like this. Okay, so that 7, 20.7, you want to read it. A biology student should read that bit. Okay, it's very important for future knowledge in your case. All right, guys, that's it. Chapter 21 has been posted, so this is the last thing that you need to see. And I think we'll meet up on Monday. Everybody will be happy. Okay, talk to you then.